Welcome to this session 6B, the importance of in-the-loop testing for model validation. This is a very interesting topic, and I appreciate Isig and Julia for providing this opportunity to talk about this. Why do we do modeling, first of all? Why do we want to study systems? It's because we want to avoid unnecessary experimentation, try and error in the field, and potentially create catastrophe. So that's why we do studies, and then that's why we do mathematical modeling of devices as much as we have information on those new technologies and systems to be able to study them in different operating conditions for different scenarios, situations, rare scenarios, just to be able to prevent as much as possible experimentation in the field before we deploy them. But it's very important to understand what advantages models have and what limitations they have. So you can see that you can perform safe and controlled testing with models. It allows you to create all those scenarios that are otherwise rare in the field, but you want to know them before they happen. It's scalable. You can create many cases in shorter time and reduce the time of your studies, understanding your system. However, it comes with limitations. I categorize them in 5 main categories. First thing is that all models are simplified and based on assumption. So basically, to create a balance between your computational and modeling burden versus reliability of a model, you need to make assumptions at some point. And this may result in some overlooking some specific phenomena or behavior of the system. So that's one thing. And then the second one is that you always want your models to be validated. This morning, in the previous session, it was also discussed that we'll see behavior from models that do not match the actual device and field because they're not rigorously validated. What is the reason for that is mostly because the scarcity of field measurements in all scenarios that you want to validate your model against, not only a steady state, not only all those normal operating conditions, but in many scenarios. And finding those measurements is difficult. Having a complete set of data is very difficult. The next one is model maintenance. So as soon as a vendor, an OEM, updates their firmware or control parameters, you need to keep up with model maintenance. And this is a very difficult task. It basically, you have to rely on close collaboration with the OEM at all time. This is a very tall task, exhaustive too. The other one that I can mention is that different OEMs, they use different tools and formats for modeling, and it makes it difficult to check interoperability of these devices in the field, especially when you're dealing with multi-vendor projects. So one other thing is that you run the models on CPUs with perfect determinism, which is not going to exactly represent what is happening in the field. There are other interfaces like communication aspects in the field that you need to consider, and they are usually overlooked in modeling, although with a lot of effort, you can also emulate those. And lastly, and basically this is a kind of a conclusion on model limitation, is that we all understand that in the earliest stages of the studies, planning modeling is perfect, best tool that we can use because it expedites things, but maybe during commissioning and later stage of a project, those limitations, they show themselves more and more. So how do we address this with in-the-loop testing? And in this case, I'm talking about hardware-in-the-loop testing. What is a hardware-in-the-loop testing first? You have on the right-hand side, you have devices that you want to test or study rather than instead of using a model of them because of those limitations or because you don't have enough knowledge about what's happening inside them, because they might be black box. These devices can span from any controller prototype, protection relays, IEDs, devices in digital substations, any inverter or converter controller, or even power equipment that you want to test. And you want to test it against a realistic system that they're going to eventually sit in. For that, you would need, as you can see on the right-hand side, a special type of simulation device called the real-time simulator that inside you can model the rest of the grid with all the equipment besides the device under test. And then it includes specialized computers / simulators that can perform those real-time simulators that eventually enables a closed real-time feedback under which you can safely test your device under test under many, many scenarios very quickly and efficiently. And how does this type of testing address those limitations? If you look at here, you don't need to do any simplification or assumption on the device under test anymore, because you're actually testing the same device with all the interfaces, with all the actual behavior of it, and arms and legs that it would have as well. You can use the same setup to create a lot of validation data, synthesize all of those scenarios, and then use it for your offline models to make sure they are validated in those rare scenarios as well, and as well as any operating condition. You don't need to be worried too much about maintenance in this sense. Your reliance on OEM will reduce to some sense, because as soon as there is a new update to the firmware or control settings, the same way your device in field will get updated, your replica or your device under test in the hardware in loop setup can get updated without additional modeling requirements or lot of back and forth between you and the vendor to get those updated models. You can also don't have to worry about interfaces and interoperability, because you're actually testing the device with all the challenges of interfacing that it has. And finally, the best use case of these type of settings is during or before commissioning, or in a safe way, so you can understand all of the aspects and challenges, address them before the actual deployment happens. Now, with this opening, I just want to introduce our panelists. I'm Reza Pourramezan with New York Power Authority. I'm a manager at Advanced Grid Innovation Laboratory for Energy. And I had to step in as the chair because our original chair unfortunately couldn't attend the meeting. So you get me, but at the same time, I'm a panelist, so I get to introduce myself twice. So I guess this is something. We'll have great expert panelists on this session. Aditya Ashok, Director of Energy System Research at Opal-RT Technologies, will talk about using hardware in the loop to improve model fidelity. Bryan Buterbaugh, application engineer with Hitachi Energy, will talk about a different type of in the loop, which is software in the loop simulation, specifically for grid forming converters, and using those practices to ensure accurate modeling. And Lucas Unruh, engineering manager with electronics, will talk about how to address challenges from the point of stability and model validation while retaining OEM model IP and confidentiality. So, I guess I get to introduce myself now again. I'll start with the first presentation. I'm going to talk about advancing power system innovation and reliability using specifically hardware in the loop. But before that, New York Power Authority, or NYPA, is the largest state-owned utility in the United States. We are transmission and generator owners. We have 1,000+ customers that benefit from our hydropower. But recently, we had an expanded authority to design, develop, and operate renewable as well as nuclear power plants. We have now about 7 gigawatts of those in the pipeline. And then the specific group I work in is called the AGILe team. We are a specialized study and testing facility. What we do is that primarily we have developed large-scale EMT models of the whole New York State transmission grid. We use them in different platforms for different studies. We leverage our real-time simulators, our hardware-in-the-loop setups to, when appropriate, test any new technologies before they go to the field, make sure they're de-risked, make sure we understand all the challenges. But today, I'm not going to talk about any specific use case at AGILe. I want to walk through the basics and foundations of hardware-in-the-loop testing, and basically talk to you about what it takes to set it up and when does it make sense, the most sense to use these type of setups. So I'm going to leave deeper examples and case studies to my fellow panelists. So consider this as a quick orientation for hardware in the loop, and then we'll take a look at that. So what are the main requirements to perform a hardware in the loop testing? The first one is you need to make a synchronized simulation between your simulator and your hardware. So it's very important that those simulators, that they can execute every time step and solve your model for every time step exactly within the real clock period of this world. So these devices, they can talk to each other correctly. I'll talk about this in more detail later. And then you're going to have accurate modeling as well as stable simulations to make that happen when you close the loop between simulation and your device under test. So your simulation needs to be numerically stable. It's challenging, and specifically when the grid that you're modeling is larger scale and it has more details in it. So this is something to consider. It's a big challenge, and it depends on what is your zone of interest when you're doing these studies. When you do hardware in the loop testing, you can only focus on the device, model the grid using an equivalent voltage source, address some issues with that, but that's an isolated testing. If you want to see the interactions of your device with a larger grid, that's when the modeling challenge comes in, and that's when your model gets large, and then you have to maintain real-time characteristics still. And then lastly, and importantly, you need to have proper interfacing between your simulator and your device, and it has to be flexible and reliable enough to prevent prolonged latencies and to make the stable loop happening. So, for example, we will see in the next slide that what it takes, what media it takes to connect real-time simulator to different devices. Now, just to give you an example of real-time simulation and what is the difference between simulations that are slower than real-time and faster than real-time. Imagine you're using an offline software for modeling. They usually run and execute a, let's say, 15-second simulation in faster or slower pace than real-time, depending on the size of the network and all the details that you put in your model. If the system is slower or faster than real-time, it's not possible to connect it to the hardware. The reason is that they are talking different languages from different universes. I'll show an example of how it happens. On the top, you can see a simulation of 15 seconds that is being executed slower than real time. And then if you try to connect it with something to a hardware at the bottom, you will see what the hardware can see is completely different. It sees 30 seconds of simulation, and the waveform is deformed to a 1 hertz waveform has been converted to a 2 hertz waveform. So the hardware doesn't see the same thing. The same thing applies to faster than real-time simulation. You can see that what is reconstructed by the hardware is different. The only way you can connect the hardware to the simulator is if the simulation is being executed exactly within the real clock, as you can see. So it will be seen completely as it was intended to be seen by the hardware. Now, there are different types of interfaces when it comes to hardware in the loop setups. Now, the main one or more common one is called electrical waveform based type of interface. Imagine an IED, a protection relay, sitting in the field. It usually receives voltage and current waveforms, sinusoidal waveforms from your instrument transformers, CTs, PTs, CVTs in the field. And they come in 5 amp or 200 volt ranges of voltages and currents. These are what we call electrical waveforms. If you want to replicate and study the same device with a real-time simulator, you will have to have such a connection. If it's connecting to the simulator, and because the simulator usually operates or outputs voltages and currents in smaller scale values, such as 10 volt or milliamp range, you would need some interfacing devices, some signal conditioning, such as amplifiers, such as transceivers, signal conditioning device to make that happen. So this type of interfacing can use for measurement control or even for power hardware loop, which we'll explain later. Another type of interfacing is when you use network communication based type of things. This usually happens in digital substation. For example, when you have a merging unit that receives the electrical waveforms from instrument transformers and then encodes them as a type of a protocol, such as IEC 61850 or any other type of a standard, and then sends those through communication links that could be either Ethernet, copper-based, or fiber to your device. Now, if you want to put this device, the DUT, or in this case, your protection relay that I'm showing here, in a hardware loop setup, you need to have your simulator be able to encode to the same protocol, and then you need to create the same link for network communication between them. So this is another way of doing it. There is a different layer of interfacing here in hardware in the loop, and that is called time synchronization based. This is not for exchange of data or measurements. This is just to make sure that you have a common time scale or common clock between your devices that are usually based on network communication. You need to ensure, for example, that your merging unit and your protection relay are synchronized, and the measurements in them are timestamps. Therefore, you would use GPS antenna, and that would be received by a network clock that will provide that time reference under different protocols, such as IRGB or PPS or NTP or things like that. So each have their own use cases. And then you have to use appropriate interface media, such as coaxial cables, Ethernet, or fiber-based connections. So, and then you replicate it exactly the same way, and you have to clock and synchronize your simulator as well. Now I want to shift the presentation a little bit towards two broad application domains of hardware in the loop testing. The first one is called control hardware in the loop, or CHIL. This is the focus here is just to test control and protection devices that have low voltage interfaces, not power equipment, such as inverters, switches, things like that. Just focus on control and protection. And it's very common. The reason is that you don't need too much equipment to make the interface happen. What happens is that on the left, you see the software environment of this setup, highlighted in blue. So what happens inside your simulator, you model the rest of your grid where your device is going to be sitting. You also model any parts of that device you're testing that is not control and protection, any part that is power, such as switching, such as any other type of transformers, such as protection devices. You model all of that inside your simulator. And then still in your interface on the software side, you will have to have some library components of your software that allows you to translate and scale or encode those measurements from the simulation, those values, numerical values, samples from the measurement to appropriate signals that is needed to be communicated to the device. Like in case of IEC 61850, you're gonna have an encoder that does that. And then everything will be passed to our input-output interface of the simulator. This is one of the aspects of a specialized real-time simulator. They have these analog or digital cards or even network-based cards that allow you to communicate with devices. But it's not all, because your devices usually operate in a little bit higher scale voltages and currents that a simulator cannot match. So therefore, you still need your amplifiers, the smaller scale amplifiers or attenuators, transceivers, etc., to make this happen. As application, I can mention one of the applications that is very relevant to this session is also validation of inverter controller and protection relays before they apply to field, because this setup allows you to perform many different scenarios that are otherwise impossible to replicate in field in a controlled environment, and then test the behavior of your controller against those events. So, and this can happen in a very efficient way, fast way. You can actually go Dr. Strange on the system in this case and create many millions of scenarios if you wish so. The other type of hardware in the loop testing involves also testing the power equipment in tandem with your real-time simulator. In this sense, you need to bring in your power equipment such as your inverter or other components outside to the hardware side of the hardware in the loop. This setup is called power hardware in the loop, or FIL. And again, you still have your grid under study modeled in the simulator. You don't have all the switching anymore because they're all being used as actual devices. One important difference here with Chill is that you cannot exchange power with your simulator, because the simulator is not designed to do that. So therefore, you need a special type of interfacing. It's called power amplifier to exchange the power between your device under test and an external grid that you need there. What happens is that your simulator provides reference signals at the interconnection point to the amplifier. The amplifier uses those reference signals to scale up and allow the device under test to connect exactly under those scenarios. And this has to be very fast and efficient. And then once the device under test reacts to this, any power that is generated by that device or absorbed by that device is exchanged to the external grid on top. You can still have your control and protection loop as well in this one. So there's a complete loop, and then all the measured power or currents from your device under test are scaled down and sent back along with your control signals back to the simulator to close the loop. And that simulator will use those measured values to complete its calculations and numerical studies. So one thing that is very important to note here is that you would need, or basically the devices that you can test with this setup are limited to this hosting capacity of your grid and the size of your amplifier. So that's very important. It sometimes gets very expensive and brings the question that when we need to do this. Now, with this, I want to just finish with the concept of hardware loop testing, specifically for inverter-based resources and modeling. Who can benefit from this? In fact, in my opinion, everyone can benefit from results of hardware in the loop testing. But who are the main users? Who are the main people that can execute this or make sense for them to execute these type of simulations? Usually researchers use it very much OEMs use it a lot for their factory acceptance testing and other development activities. There are many examples of utilities and system operators and plant developers or even solution providers that perform these type of studies. How do you want to do this in the space of IBRs? One idea is to provide the control and protection replicas, which are the exact hardware copy of your actual control in the field. What happens in the field, you can see that you have your plant, it's connected to the grid, and it has some cabinets housing control and protection. If you want to make a parallel environment in a simulation lab, what you need to do is to model the grid, model your hardware, and connect your simulator to this replica. So at the beginning or at some point of the commissioning, you need to have these replicas in that lab. You need to have the lab set up, and you need to have a model of the grid you want to connect to created for this. So again, the question comes, who should do this expensive and highly expert requiring job? There are a lot of examples of this happening. Actually, this morning we saw the Chilean operator doing this, and REL is doing a lot on control hardware in the loop and as well as power hardware in the loop. I have listed a few of these people that are in the utility space and are doing this type of applications. It spans a lot. You have it in HVDC commissioning, IBR testing, fax devices, protection relay and coordination testing, many other different applications. I want to skip this slide, which is basically, I think Aditya will cover this part on the advantages of hardware in loop when it comes to compared to offline software. So, but I want to just enumerate some of the potential some of the challenges that hardware in loop can potentially address in the IBR domain. You can see pre-commissioning, you can perform interconnection compliance testing with this very safely. You can have and basically increase your confidence in your new protection and control algorithms or solutions. You can reduce commissioning delays by using the system to draft your commissioning testing, understand what you need to test during commissioning beforehand. You can also test all the other aspects of other than protection, because now you're interfacing them actually. So all the interfacing aspects, communication aspects, cybersecurity, that can be tested. And post-commissioning, also, this can be used for any playback and recreating of events for post-mortem. You can use these devices for in-house training of operators and engineers. You can reduce maintenance downtime. Anytime that a software or firmware is upgraded, you can first test it on your setup before you actually go to field and create potentially mayhem. And then this can also be used for long-term maintenance and monitoring. As Julia was mentioning, do you have monitoring devices for IBRs? You can use this to generate validation data for your models, for continuous monitoring and of your plant. Basically, you will have a digital twin of your device running in parallel with your actual field deployment. I'm going to skip this one as well. I just want to wrap up by looking forward and see if we want to address some of these shared challenges that system operators, utilities, and OEMs have in model validation and maintaining model accuracy using hardware in the loop because of those awesome capabilities that it has. But at the same time, knowing that performing this type of simulations requires a lot of investment, requires a lot of expertise, time, and effort, at least to create such a facility and then maintain it. How can we collaborate and exchange knowledge to making hardware in the loop more accessible across the industry? Because I think, as you can see in the examples that I showed, it's a very good, effective way of at least ensuring that new technology, when it comes to the field, before everyone is confident about it, is tested in such environment. With this, I'll give it to Aditya now for more in detail use cases on hardware. Thank you.
Thank you, Reza, for the great primer on hardware in the loop. Hello, everyone. So I'm going to tee off from where Reza left and dive a little bit more specific into hardware in the loop testing, particularly in the context of, let's say, power plant controller validation, right? So we're going to see how hardware in the loop testing can improve fidelity and accuracy in this context. Just a little bit before we dive in about us, Opal-RT Technologies. For those of you who are not familiar, Opal-RT Technologies is a company that enables hardware in the loop testing by providing real-time simulation hardware and software. Company is founded in 1997, headquartered in Montreal. We have offices around the world. Primarily are involved in development of hardware in the loop testing solutions for power systems and power electronics. We are involved in a lot of application areas ranging from microgrids to bulk power system, electrified vehicles, electrified ships and airplanes as well, right? So that's about us. So let's dive in, right? I don't need to preach to you guys. We all know that with the interconnection of inverter-based resources across the grid, and also we're seeing a lot of large loads that are leveraging power electronics-based resources. The grid dynamics is changing. Interactions are becoming faster and faster. We are seeing interactions that are not captured by existing models in the field. And if you look at disturbance reports from NERC, they actually highlight several inadequacies in model validation, in factory acceptance testing, as well as in overall in model quality testing protocols, right? What are some of these factors? You look at things like incorrect settings or parameters, simple things like that. And then we also have things like failure to model specific control and protection behaviors, right? So this is all something that can be fixed. If you look at the interconnection process as well, lack of adequate testing leads to expensive delays because you bring and assemble a bunch of different devices from different vendors. You start seeing practical issues and interoperability challenges, which could have been weeded out if you were doing testing, right? And if you delay things during commissioning, you're going to result in, you're going to have a lot of penalties costing several thousands of dollars, right? Hardware in the loop testing is essential to ensure that you can not only do this easier, but you can also do proper model validation so that you can have trust in your models moving forward. So I want to talk about hardware in the loop testing in the context of, let's say, the IEEE 2800 or any kind of standard conformity assessment process, right? If you start all the way at the beginning at the OEM side, on the top left, OEMs develop a product and then they do lab type tests across a range of scenarios to ensure that the models that they produce are representative of the actual product, right? So this is an area where definitely hardware in the loop testing is used. And this is what is used to actually validate the unit models for the inverter level controls, right? And typically this is what gets delivered as a black box model. So IBR unit validation is also a step where hardware in the loop testing plays a role. Now, if we move forward, people then use the models that are provided and assemble and build together a plant model. And this is the model that undergoes design evaluation for compliance for specific grid codes, depending on the system operator that you're connecting to. Again, people are still using unit models that were validated and assembling plant models, right? And then they submit and it goes on to as-built installation and evaluation, right? And this is where you are getting closer to commissioning. And this is an area where potentially hardware in the loop testing is useful. We are seeing people already using hardware in the loop testing to de-risk, and I will provide an example of one engineering firm that used hardware in the loop testing to actually save a lot of money during the pre-commissioning and commissioning stages, right? And now commissioning is done. If you move on and commission the plant, and then you see some events happen in the field, you can also use it for post-commissioning model validation, right? You collect data, and then you try to replicate things on a real-time simulation setup with hardware in the loop. You can also ensure that if you have any discrepancies, you can fine-tune your model and true it up, right? And then this can be a continuous process where You periodically collect data to ensure that your model is still representative, and you can do this with hardware in the loop, right? So this is just to give a context about what parts of the overall process you can involve hardware in the loop testing. Now, again, I'm going to have a similar version of a picture that Reza presented, but this is somewhat contextualized for the IBR context, right? If you think about an inverter-based resource, you are typically modeling it within the real-time simulator. It could be any type of resource, and then there is a grid interface. And then if in the context of inverter-based resources, you could either have the inverter-level unit controller as an actual hardware that is connected and interfaced to the real-time simulator. In that case, the inverter controller is getting signals, voltage and current signals from the real-time simulation through the analog and digital cards that are there. And then it is producing the gating pulses that go back because the inverters are modeled within the real-time simulator, right? Now, if you think about power plant controller, oftentimes the inverter level unit controller is sitting as a black box within the real-time simulator, and you are exchanging signals to the power plant controller. Now, depending on setups, sometimes the meters may be modeled within the real-time simulator, or you may have physical meters that are external, in which case, again, you are sending voltages and currents to the meter. And depending on the meters, you may or may not have signal amplifiers that raise the signals to the levels that the meter requires. And then the meter is going to communicate that information over a communication protocol. If you think about protocols like Modbus or DNP3, these are typical protocols that you see. The meter is communicating information to the power plant controller, and then the power plant controller again is going to respond back, sending set points to the real-time simulator, right? Oftentimes, communication network is not modeled here. People assume standard delays, but this is also something that we have seen people doing where you can also mimic and model the communication networks in greater detail because we are starting to see network latencies often play a role in closed loop stability as well, right? So with a setup like this, overall, you can validate your unit controller model. You can also look at the plant level protection right through behaviors. You can look at coordination issues between IBR unit and PPC. And I'm going to show some examples of what this looks like, right? So before we go into examples, I want to talk about general testing considerations and what you can see with control hardware in the loop, right? Obviously, you can detect modeling issues. If you see something not modeled quite right, when you compare results between your hardware in the loop test and your software model, you're going to see things, and then this is going to help you understand that you haven't modeled something correctly, right? You can detect configuration issues. Let's say that you have a model that has a particular configuration, and then the actual product or the PPC hardware has something else. You can detect that. You can also detect things with measurement and meters, right? Meters are often sampling data. For example, commercial meters may be sampling, let's say, 128 samples per cycle. And this is going to result in calculating the value. So if your simulation model does not mimic the same behaviors, you're going to feed different signals to the PPC, right? And this sampling and the signal processing that happens on the meter is also important to capture, right? Next thing is in terms of communication. Now there's different things here. One is the network latency of the communication between the meter and the PPC. There's also the network protocol. So if you think about Modbus, you are operating under a pole response regime. So depending on the settings of the device and the polling, you're going to have a delay added there. And then each device, including the meter and the PPC, has its own processing cycle. So you will have delays that are there in the closed loop that you need to account for, right? And if you think about the controller or the PPC itself, the hardware is typically some kind of PLC-based platform. It has a cycle time, so it's periodically doing things repeatedly. So you have to account for the cycle time of the PPC, right? So all of these could play a role in influencing how the model behavior is with respect to the actual product, right? So you need to be actually looking out for these things and ensure that your model is able to capture as many of these things as possible, right? So now we'll start going into examples of actual setups and show how this helps, right? So this is an example of a PPC controller hardware in the loop setup. We have a real-time simulator connected to a couple of different variations of PPC, right? And the picture on the right is an example of the test system. We have 16 inverters here, and all of them are modeled within the real-time simulator, including the metering setup. and we have the physical PPC exchanging signals with the real-time simulator over Modbus protocol, right? So that's it's a very, very simple setup. And I want to show a couple of examples of behavior that you would see in the field, right? So if you look at an active power ramp, right? So you get a set point from the PPC. The actual inverter model takes time, right? And you actually see this staircase kind of response in the bottom plot. This is actually reflective of the manner in which things are processed, right? Every cycle time, the PPC sends a new set point, and then it goes to the real-time simulator over Modbus. So you actually see this steady response in the field, right? This is how you should expect to see your model also ramping up, right? If you see a model having a very smooth behavior, then you're not probably capturing something, right? Again, similar thing with the voltage step. If you change the grid voltage, if you see the bottommost plot, that is a plot of the reactive power, and you can actually see similar step behavior of the PPC sending set points and then contributing to reactive power, right? Another example, so this is an example of plant level hardware in the loop testing during the pre-commissioning phase. Now, in this case, again, the grid model is on the real-time simulation. And in order to feed signals to the PPC, we have a signal amplifier that is pushing out the signals, the voltages and currents to the actual setup, right? And then the PPC is sending commands back over Modbus, right? So this is an example of what you would see if you did something correctly, right? This is an example of results for a voltage reference step test. Now, in this case, we actually have three things. Typically, you would only try to true up your simulation model with hardware in the loop. In this case, they also had measurements from the actual site, right? So that is the actual reality. Red plots indicate the field measurements from the site. Blue plots indicate measurements from hardware in the loop, and then the green is the trace from the simulation tool, from the offline simulation tool, right? If you actually look closely up at the plot on the right and the voltage, you can actually see for the field and the hardware in the loop, similar kind of step response indicating this cycle behavior, right? Every cycle time, you're getting a new measurement and the model is adjusting, right? So this is how it would look if you did things correctly, where your simulation model is closer to hardware in the loop, and hardware in the loop is again closer to the field, right? So you actually see that hardware in the loop is a good surrogate for actual field testing, and it's much more closer in reality to the actual product behavior, right? So this is what you should be looking at when you are doing this correctly, right? Now, what are the things they encountered, right? All kinds of things that we talked about, right? Controller hardware cycle time mismatch. If you don't model it correctly, you're going to have a different response, right? Delays due to metering configuration. So if you don't capture how the meter is processing things, you're going to have a problem, right? Failure to model equipment. In some cases, especially if you have complicated setups where you have hybrid plants, there may be multiple PPCs and multiple controllers. If you don't account for them, you're going to have extra delays that you have not considered in your model. Obvious things like PPC model versus hardware mismatch, right? You may have something in the model that doesn't actually exist in the product. This could actually result in performance issues, right? Parameter conversion issues. For example, in the product, you may have things in actual units, and in the model, maybe you have something in per unit, right? This kind of issue will also cause differences, right? I talked about communication, right? You assume a standard delay in the model, but sometimes the Modbus delays could be variable, right? It could be anywhere from 30 to 200 in this case for this particular testing scenario, right? Incorrect measurements, of course, and when you integrate things from different vendors, you're going to have interoperability issues, right? And sometimes you also identify dynamic response issues because there is a mismatch in some control parameter. And this is also something that you can catch and correct, right? And of course, if you have different firmware versions, you're also going to have different behaviors, right? So all of these are real world challenges that you can catch and address with hardware in the loop, right? So if I have to sum it up, hardware in the loop testing, as you saw, is essential to ensure that your unit level model is validated as well as your plant level models, right? It is valuable across different stages to catch things like modeling errors, incorrect parameters, performance related issues, impact of communication, right? And it can be applied at any stage in the life cycle, right? Or a lot of stages in the life cycle, I would say, from the initial stages at the OEM level, as well as in the late stages in the pre-commissioning as well as post-commissioning stages, right? So that you can continuously maintain your models. And if you think about the interconnection process from an economical standpoint, hardware in the loop testing is an easy way to de-risk project delivery and ensure that delays are minimized during commissioning, thereby minimizing any penalties that you may have, right? So with that, I would like to pass it on to the next speaker. Thank you.
Hey, hi everybody, Bryan Buterbaugh, application engineer with Hitachi Energy, supporting fax technologies in the North American market. These days, that's pretty much StatComs, I think. Series capacitors, thyristor controlled series capacitors, synchronous condensers, StatComs with energy storage are right on the horizon here. So that's a little bit about me. I have this marketing slide, but I'm not a sales guy. I think it does represent well a lot of the things we see in the power system today, some of the challenges, some of the initiatives, and I think it highlights well the relevance of fax devices that comes. We see a lot of different applications for them as we address some of these issues and goals in our power system. So a very relative topic, and I think we have grid forming mentioned sort of in the title here. And I've seen some presentations today, this week, talking about grid forming with battery energy storage. And I think a lot of times when we talk about StatCom with energy storage capability, enhanced StatCom, we get sort of the response, grid forming is going to be so great when we get some enhanced StatComs in service. And I think that's absolutely true. But with conventional StatComs, grid forming is very much being implemented and is here today. I think this shows sort of this change over history over time. Since 2022, 2023, the green or the grid forming installations, basically the grid following installations have stopped for StatComs for us. And so we're just full steam ahead with grid forming. And yeah, there's a lot of those in service. I would say close to 30 today in service, and that number will probably double here in a year or two. So very much here today, and a good control method that we're seeing. It has a lot of benefits, and we'll talk about how that has some implications for how we use software in the loop and hardware in the loop. Just to sort of take a step back and talk about how we use control hardware, maybe during a typical project. We absolutely use hardware in the loop testing. All right, we have hardware with a control system, and it needs tested. So that this isn't a presentation to suggest that we should move away from hardware in the loop testing at all. Right, we need that, but there's also a lot of upfront testing. I think as in the last 15 years or so, I've seen that with an SVC or a StatCom project, there was some study work done, maybe in PSSE or PSLF, some dynamic performance study, but it was more or less just a verification that the sizing was correct. And as the system has gotten more complex, and as we've seen different issues and different applications, we've seen a lot more of this EMT related dynamic stability work. And so we see that today. This references PSCAD, but it could be any EMTP software. But we see that there's a lot of that sort of study work upfront in a project, long before the hardware is actually implemented or manufactured. And so we have all of this study work that's done upfront. And so it's so important that that model that's used that upfront study work is accurate. And I guess what we're presenting here is with software in the loop. It's more than just close. It's exact, right? And so it's so important that that's the case. And I think that on the right here, asymmetrical faults, I think maybe sometimes this is taken for granted a little bit when we talk about a StatCom, but the way you represent a StatCom, an MMC device in a model is important. There's unbalance that develops between phases. There's unbalance that develops between individual components in a single phase branch of an MMC device. And so there are some ways to represent these devices where that's sort of overly simplified, right? One branch, one entire phase leg can be represented by one DC capacitor, right? And so that's an oversimplification, right? And even if you didn't have software in the loop, even with hardware in the loop, like that oversimplification could be inaccurate. So we're really advocating here for accurate models that are representative of what's really there, and it has impacts on the performance of the devices. So just to talk a little bit about what we mean by software in the loop, I think we have a left and a right sort of division here, where we're sort of trying to do the same thing. But on the left, we have software in the loop, and on the right, we have hardware in the loop. Basically, we have control logic, and that control logic can be implemented in real hardware. Like that's what's actually in an installation. It has some I/O, right? And so when we test hardware in the loop, we're basically testing that control logic in its actual hardware implementation. And then we're using a real-time simulator or a real system, right, to represent parts of the StatCom, for example, that can't be physically represented in a lab environment, right? So the valves, right, the transformer, there's a lot of components, surge arresters, right? Those can't be tested in a lab environment. So the real-time simulator represents those, and it also represents a system model, a power system, right? So the hardware is in the loop because it's in between. It's the real hardware, but it's in that loop. What we're talking about with software in the loop is sort of the same thing. But when we put this control logic into this model, it needs to be accurate. And so what we can do is we can take the actual control logic, and instead of implementing it into hardware, we can implement it into software. And so when we have an RMS simulation or an EMTP simulation, we're still doing the same thing where we're representing the power system and are representing some components of the StatCom, for example. But we have this actual control logic, the actual control code, and we've compiled it and we've used it in this environment. So we actually have the real control logic in the loop, right? It's just that the loop's a little bit different. So that's what we're talking about when we talk about software in the loop versus hardware in the loop. Okay, good. And so I alluded to this a little bit with the previous slide, but this is really important for MMC because asymmetrical faults create some singularities. And so these need to be represented regardless of whether you have hardware in the loop or software in the loop, but they directly impact performance. So depending upon the topology of the device, if it's delta connected or if it's Y connected, this has an implication. And so when you have a fault type that's asymmetrical and you have this topology, you're going to end up with a singularity. And so it's really important that the individual components are modeled correctly and accurately. And that, again, has a direct impact on the performance. So to advocate too, regardless of how you're modeling these devices, this part of the system needs represented accurately. Okay, so if that last two slides ago, if that was sort of the hypothetical way to use software in the loop, this is a more practical way. Like this is how we would actually implement it. And so this is an example of a PSCAD model where we have actually taken the control code. We call it MAC. That's our control platform that we use for HVDC and StatCom. But we can take that actual control code and we can compile it and we can use it, and then we can use that just like we would in a real hardware environment. We can use that in a software environment and use that in PSCAD for those types of studies. So that's what we're talking about here. That's how we would implement this software in the loop concept. So what are the implications? Well, I have a whole bunch of words on this slide. I won't read them to you, but basically, when you think about a project and the timeline, let's just say over a year and a half or 2-year process, we're progressively building something that we're going to implement in the field, right? And so there's so many tests and simulations that are done at the beginning of a project. And so, yes, we still need to test the hardware at the end of the project, but do you really want to wait until the end of the project to test all of these performance functions? And what are the implications? What if you get to the end of the project and you run some tests and there's some differences in your model? What does that imply about all of the simulations you've done a year ago? Right now you have hardware implemented, right? You have a control panel that's already finished. You're testing it. And you realize that all these studies you did a year ago need adjusted a little bit or modified or tuned. And so it has big implications when we're talking about the phases of a project and the timeline. And especially these days when everything is so critical time-wise, right? We're in a race to get things installed. So this concept of when to do things and what to use to test things is really important. And software in the loop really allows us to be confident that what we do in the initial stages is going to carry through. All the tuning we do, all the studies we do, all the elaborate things we look at with different scenarios in the power system, interactions with other devices, that's all going to pull through. And then when we actually get to the factory and we're testing the hardware, because we're still going to test the hardware, now we can focus on what's important to actually test and verify that hardware and less about all the performance things that we've already considered. And then the last bullet, we think about after the hardware leaves the factory and it's installed. This talks about during commissioning, but even after commissioning, so much of the benefit from a power electronic device is that it's parameterized, right? And so if the power system changes, something changes in 5 years or in 10 years, there's parameters that we can go in and change and adjust. And so if you have this actual code in the loop, right, now you can do that with confidence. You can adjust, you can make changes, and you can be confident that those changes are going to be reflected in the actual hardware when you make those changes in the field. So there's a lot of different benefits across all phases of the project and the timeline there. Yeah, this is a nice slide too. I don't want to steal, I think Lucas probably has more, can share a little bit more about these, but lately, model limitations, we want to model more. We want to look at different interactions. We need bigger models, more accurate models. And so there's a big reason why we need an accurate model that's in a software like PSCAD. Then there is trying to represent that in a device that can only model so large. And so we've seen this trend, and the trend is not going away, not going anywhere. So that's just another reason why software in the loop and an accurate model is so important. Okay, so yeah, grid forming specifically, what are the implications here? I have this wheel of services that I've been talking about. When I think about what it takes to make a grid safe and stable and secure, we sort of associate all of the services that have historically come from rotating machines, from synchronous condensers. And so we associate those services with synchronous condensers. But what we're seeing is that we're sort of losing those synchronous machines, right? And so we're losing some of those services. So how do we provide those services to the grid when we're replacing synchronous machines with other things like renewables and DERs and so many other things that we see on our system today? And the answer is that grid forming is really allowing us to provide a lot of those services that used to be there from a synchronous machine. Now, we can't provide all of them with a conventional STATCOM, let's say, but we used to always think of an SVC or a StatCom as just sort of this bottom right quadrant that was voltage control. And it's more than that now, right? So I just listed some services that it can provide. Do you need fault current? So a machine can provide more fault current on a per unit basis, sure. 3, 4, 5 times it's rated. But that doesn't mean that a grid forming StatCom can't provide fault current. It can only provide 1 per unit fault current, but that's still providing fault current. So if you need fault current, maybe you need a 250 megavar StatCom instead of a 70 megavar synchronous condenser, but that's a comparable amount of fault current. So now we have a grid forming StatCom that can provide something that historically it wasn't used for previously. Maybe you have too much fault current, right? And so you don't want fault current. You can still use a GFM StatCom and you can reduce that because it's a parameter that you can adjust. These control works extremely well in weak systems, right? So we have really weak system, islanded systems, or maybe we just want to help support with system restoration after a black start. So the grid forming StatCom can help with a lot of those different scenarios. Damping at high order frequencies, maybe you have a really strong system and so you're starting to lose some of your damping at the high order. Grid forming inherently has some damping at those high order frequencies. It has some inherent damping at subsynchronous frequencies too. So where do you have an oscillation? Is your oscillation 25 hertz or is it 15 hertz? You need grid forming and you need to tune that model to see what it can do. And so all of these services that grid forming can provide, there's all sorts of studies and phenomenon and scenarios that we want to consider. And we want to consider those upfront, early in a project. We want to make sure that this solution is solving those problems. We want to understand that this solution can work, for example, instead of a synchronous condenser. We want to learn that right away up front. We don't want to wait until we're testing it in a factory a year from now. And so even in the tender phase, we might want to see some of these capabilities. But then when we talk about what grid forming is and how it's defined, there's not necessarily a universally accepted definition. So I think that's another reason why we want to see how this performs with an accurate simulation model and not just take someone's word for it that they have grid forming and it can solve all these problems. So like, how does it actually solve my problems? We have some concepts, right? So when different organizations, different standards are written, they have a similar idea, right? There should be sort of an instantaneous response. It should behave a lot like a synchronous machine or an ideal voltage source. We want the negative sequence injection. It should ride through step changes to voltage and angle. So we see sort of, we like grid forming, but it's not necessarily absolutely defined yet. And so when we talk about a tender and we talk about demonstrating a device's capabilities, we want to know that upfront and right now. So I think this really lends to having a good, accurate model and why we're advocating so much for software in the loop. Yeah, so just to highlight, how do you demonstrate that you have grid forming and that it can solve your problems? So these are just some of the things that we see that need to be demonstrated, maybe even in a tender, right, to show the effectiveness of this type of an installation. Okay, I have some plots, because what would a presentation be without plots? In this case, we tested our software in the loop. And so we have a situation here where we were taking some measurements during commissioning, and we had a trip during energization because there was a conventional relaying setting that needed to be adjusted a little bit. There was a mistake there. But what we saw, I think we could have done a little better job of matching up these axes a little bit. But what we see is that these are nearly identical, right? So this is something we were able to replicate from the field to show that what we have software in the loop matches what we actually recorded at site. So we have this really close, accurate representation. We even see that this incorrect settings cause the same exact result. So then what we're able to do is we're able to go adjust those settings. We're able to rerun this contingency, and we can see that those settings changes effectively alleviated or fixed this problem. So we were able to do that with confidence. So here we are at commissioning. We're not trial and erroring, right? No one wants that, but we can accurately adjust the setting and know that it's going to be effective and work. So, this has implications. In this case, it was just during commissioning, and it really didn't have anything to do with the STATCOM controls. It had to do with some conventional relaying, but we can see the implications. If something changes in your system 5 years from now, right? We want to have this confidence that we can go and tune things and make adjustments and know that they'll be correct and accurate. I have this is sort of just a conclusion with some pros and cons. I'm not going to go through all these. I don't think there's really anything new in here that I didn't already talk about, but maybe just to highlight a couple clear takeaways. There are absolutely implications in the timeline of a project, and sort of a delineation between what should be used, hardware in the loop versus software in the loop, for certain types of performance requirements and functional testing. So the idea is that we're using RTDS for functional tests, hardware in the loop for functional tests. But when it comes to evaluating system performance, we want to do that with an accurate software in the loop model. So I think that's the big takeaway from this, and how important it is that that's an accurate model. Yeah, okay, that's all I have. Thanks.
Good morning, everyone. My name is Lucas Unruh. I'm a consultant with Electronics Corporation. We're based in Winnipeg, Manitoba, and we do a lot of work in EMT simulation domain. And yeah, first off, thank you to Julia and Isaac for having me, and thank you to Reza for chairing, and to the rest of my co-panelists. You've all done a really great job. Today, the topic I'm going to present on is going to be a little bit of a shift in focus from what we've been talking about so far, and it kind of carrying on from what Bryan was presenting in terms of the software in the loop concept. And what I'm focusing on here today is offline EMT studies where we have multi OEM, lots of different models in our system models, some of them from different OEMs, right? So as we know, a lot of different entities out there are performing EMT studies today regularly by ISOs or TOs or consultants. And a lot of these models that are going into these EMT studies are real code models. And that's kind of another word for software in the loop models. And these models also, they might have been validated using some of the hardware in the loop methods that we've discussed as well. And what this means is that these models are usually received under NDA, and that the OEMs really are very careful about the distribution of these models. Specifically, OEM A doesn't want the model going to OEM B a lot of the time. So that, when we take a lot of these models and put them into a single system model and start to look at different types of stabilities and things like that, we need to get the OEMs involved in tuning their models and making them work in the system. But it presents a bit of a challenge when we have to maintain that OEM confidentiality. So that's kind of the concept of what I want to address here is how can we effectively bring the OEMs into the loop when we're performing large EMT studies which have multiple OEMs in the systems. So just a little bit of background on the typical EMT study process. This is really high level. So you're going to start it off with some sort of study trigger. Could be an interconnection study, event replication, or just a periodic stability study. And one of the first steps you're going to do is to try and obtain high quality, real code, verified models for the EMT devices in the system that you want to consider. And again, hardware in the loop plays a part in making sure those models are as accurate as they can be. And from there, the EMT study engineer is going to take those unit models or plant models and construct a system model from them. And really, this is a lot of the work here, right? Taking those models, stitching them together, automating your contingencies, and then Once you're happy with how the case looks, you run all your analysis. And from there, you're going to probably find a bunch of issues. Well, hopefully none, but usually you do. And you need to find some way to move forward, to mitigate. And often the lowest hanging fruit or the cheapest option is to do control tuning on the devices that are showing issues. And there might be there's often some iteration there. So yeah, you can imagine you've done a whole bunch of work, setting up your system, running your study, and then you get to the point you see some issues, you tell the interconnection customer or whoever, device is having the problem, we're seeing issues XYZ, and they immediately will say, please send us the system model. We need to analyze it, with everything in. And right away, you're in a very uncomfortable spot because you can't do that. You can't send them a system model. So what do you do now, right? So there's a number of different approaches that we can take to bring the OEMs into this loop here, in terms of helping them to get the information that they need to be able to tune their models. And I'm going to present 4 different approaches here, and they're sort of increasing in complexity in some ways. And the idea here is that you may be, some of these methods may be overkill for the problem that you're having, right? So you kind of perhaps want to pick a method that is appropriate to the kind of problem that you're seeing in the system, and hopefully I'll be able to help you, frame that a little bit better. And then, before you start on any of these, just remember that EMT models become stale quite quickly, especially during the planning phase. So just make sure you're using the right IVR model for the plant that you're studying before you kind of go down any of these routes. So the first method is pretty obvious. You just run the study and send the simulation results out to the OEM, and they'll say, can you give us the model? You say no, and then you just give them whatever they ask for in terms of the actual simulation quantities that they want to see, system stuff, or maybe some internal quantities from the plant or something. And this is, and then they go ahead and try to tune the equipment based on that information as best they can. A lot of the time there's really long time lags between, in terms of just exchanging emails, time zones, potentially language barriers, and them just doing that sort of tuning on their own end without, basically somewhat blindly doing the tuning, right? Because they don't actually have the system model. This may be appropriate when the issues can be mitigated in a pretty straightforward manner, and when the OEM maybe has experience with correcting a similar issue in a different region. So if it's not a particularly system dependent issue that you're seeing, then this still can be effective. But if it's any sort of interaction between devices or a grid plant interaction, then oftentimes this is not effective, or it takes a really long time. And when I say a long time, I mean, this could take many months to resolve in some cases. The second method here is what I'm calling POI playback. So the concept here is, do you have your full system model in your EMT program, and you record the instantaneous voltage at the POI using a high resolution recording, and you save that to an output file or something. And then you take that same case, you strip out the entire grid model, and just, instead of the grid model, you put a playback model there, and you just take that measured voltage and you play it into the POI. And if you've done your sampling correctly and your playback correctly and your initial conditions correctly, you should get the exact same result that you got in the full system from that plant, but without the grid. So then you can safely send that to the manufacturer, and they don't get any system details from that. There's a couple pitfalls here. One is that the simulation may become invalid if you change the behavior of the device substantially. Remember that this is effectively an open loop test. There's no sort of interaction that you can model in this method. And there's a few instances where this method can be effective. One is where the issue can be resolved just by the OEM being able to in detail investigate all the internal quantities of their plant for a specific voltage profile effectively on the system. Or when the grid is relatively strong and there's minimal sort of like plant to grid or plant to plant interactions happening, because that sort of thing can't really be captured with this method. So if there is those sort of interactions, then there's not, you know, there's limited value in this approach, I guess. Third method is simplified system. This is another approach that can be useful in some cases. So if you kind of can look at the issue that you're seeing in the study and say, you know, we think it's mostly this specific plant that's causing an issue. So let's just try taking all the other plant detailed models out of the case and seeing if we still get the same problem. And then maybe we can send that sort of simplified system to the specific manufacturer for them to have a look at. So this works sometimes, but there's a couple sort of like pitfalls with this strategy as well. One is that the study engineer can end up putting a lot of time into trying to reproduce the issue in the simplified system, and they might not be able to actually reproduce it. So you can fail kind of from that standpoint. And then the other thing that can happen is you can send it to the OEM. They actually fix it in their simplified system, but you take that tuned model, you put it into your full system and it doesn't work. So you're kind of back to square one after having done a lot of work to get there. So there's a couple notes on that one. So the last one here, and this is really what I want to get to with this presentation, is this concept of simulation lab or virtual lab. You can kind of call it what you want. I don't know if we really have a great formal name for it yet, but this is a method or a service that we've been working with at Electronics for a few years. And the way this works is that we set up a machine with a virtual machine on it. So we take one of our big sort of thread rippers or big CPUs with a lot of cores on it, and we configure a virtual machine on that computer, and we put all of the required simulation software to run an EMT simulation on that virtual machine. And then we allow like the OEM to actually log into that virtual machine through an encrypted VPN, and they can have access to basically just a parallel processing connection in the EMT program. So, you know, you can imagine that they just see, all they see from the virtual machine is just the POI and some data transfer, and they have the, you know, ability to run the case, etc. But then on that machine, on that same machine, the study engineer will then model the rest of the system, not in the virtual machine, on the sort of firewall side of the virtual machine, let's say, not of the machine, sorry. It'll get clear with the diagram. But yeah, and then that detailed model, the system model, contains all of the other OEM device models. And so that, you know, that sort of provides a firewall to both sides, right? The system model can't look into the virtual machine, so the OEM can really model, you know, they could even go to the extent of using like open source models or open code models. They don't necessarily have to be black box even at that point, because we can, you know, they're the only ones who can have access there. And likewise, the other way around, the OEM that's in the virtual machine can't see anything into the system. And this isn't like a purely automated process. Like we still, you know, the study engineer would have to set up set up the system model and program contingencies and things like that into it. But in the end, this allows that OEM who has access to the virtual machine to iterate their control tuning as much as they want, right? And, you know, basically tune until they get the thing working. There's other applications here, but this is the one I'm kind of rolling with for now. And yeah, just to show it in a diagram here, this whole big green box here is a physical hardware, and we can set up, I'm showing a 2 OEM setup here actually, where each one can have access to a virtual machine on that computer. And we, as a study engineer, you'll actually take your system model and you'll, you know, in this case, we're going to clone it twice, and we'll have 2 sets of that running and then the OEMs can independently tune their models using, you know, by remote accessing into the virtual machine. and parallel processing to the full system model. And the full system model is, in this case, wouldn't be accessible by either OEM. And then from the actual virtual machine perspective, this is kind of like what it would look like. You have some case controls to launch the simulation. You have some communication connections to the system where you can select contingency number and things like that. Maybe you can even enable or disable a nearby plant. And then, of course, you have your electrical connection to the system. And as you can see here, all that component at the bottom of the screen is just a parallel processing port that you can't look beyond. So you just get the POI to connect to in terms of the system model. And yeah, so we've used this method, as I mentioned, a number of times to solve problems in studies that we've ran. So it really kind of kind of the poster boy for this would be an SSCI study that we ran a little while back, where basically SSCI is a phenomenon that involves IBRs interacting with a series compensated system, and the nature of the instability is hypersensitive to the IBR controls. So you can shape the damping and the actual resonant frequency with the IBR controls depending on the sort of impedance characteristics of the device. So this is kind of a very very applicable use case for this method. So the way we ran the study is that first a study engineer went ahead and configured that simulation lab using the latest models that the OEMs provided us, and then the OEMs kicked off two parallel tuning efforts using their models, whatever they wanted to test inside their virtual machine. So they ran, I guess we probably gave them a couple of weeks to tune their models. And then the study engineer takes those tuned models and kind of reperforms the full system study to see whether indeed we're getting a stable result at that point. If not, then they'll go ahead and take those latest models and inject them back into the simulation lab, and the OEMs can repeat that tuning process. So we have sort of an outer study loop wrapped around this inner OEM control tuning loop. And yeah, if things work out, then the study is complete. So I think in some studies, this outer loop still does have to run a few times. Like, I think we had to run 5 or 6 iterations for this specific study. There's some other applications to this method. One is HVDC or FACS dynamic performance studies by the OEM. So if you can imagine 2 StatComs that are maybe connecting in a weak system with different vendors, and when the one vendor has to consider the other vendor when they're doing their control tuning or maybe even their control design. So they might, if you set up the simulation lab, you can let them do that, iterate that testing in that full system context, and whatever other devices are in the system can be modeled as well. Another thing you might have heard of before as well is the AMO interconnection tool, where AMO will basically say, before we do any study, we'll expose this POI to you, and you can go ahead and model your plant there. And before we run any studies on our end, you can go ahead and do some pre-interconnection studies to just check how your prospective models are going to run at that point. Now, we sometimes get the question, why don't we do something like this for every plant in the system? It is still a fairly heavy lift to set up this sort of simulation lab for any given time. It's not a particularly automated system right now. It might be automated in the future, but not at this point. So it is, it would be overkill to do this for every project. And really, we typically only use this process when we're somewhat backed into a corner and there's no other solutions. And the last one, I'll just say the simulation lab environment sort of as a service. This one is not actually basically we would just offer the virtual machine as a virtual machine, and then whoever of our customers wants to come and drop in whatever models they want to and run them on the VM, we can let them do that just to overcome some of the simulation environment, licensing, firewall, IT complications that their organizations might have. So that's kind of just a thing that we offer as a service. So What's next, right? So right now, Simulation Lab is an available tool for solving unresolvable complex tuning issues. And as we all know, our future studies are going to continue to get more complex as we add more IBRs and large loads and series compensated systems to the system. So it's kind of an open question. Are these methods that that we're using right now, are they enough? Can they be scaled to really more complicated systems? We don't know. Probably we're going to need some help, right? So some other potential solutions which might come along in the future is potentially of loosening of NDA restrictions, perhaps open source models. I know some vendors, some new players in the inverter space are kind of promoting that. Strong model sharing requirements coming down from regulators is another potential thing that might happen, because this is going to continue to become a real problem for folks who are doing these sort of system studies with in EMT. And then last point here I just want to make is that as I kind of mentioned, like these sorts of, when we have to go to these extents, right? Like right now, it's sort of when we have no other solutions to the problem. And these cases are, we have like really complicated systems now in some cases, especially when we talked about series compensated systems, and really, we're the engineers on the ground trying to make the systems work as best as we can, but we're kind of like have been put into the situation, by some high level decisions that we don't have a lot of input on, right? So I would just, advocate for, common sense screening ahead of time and a little bit of a thought into system design just to make sure that we don't get put in this position too often where we have to go to these lengths. Yeah, that's my presentation.